welcome to covalent bonding. We spent a good deal of time talking about electrons being gained and lost. We actually spent a ton of time really focusing on ionic bonding. Covalent bonding is a different type of bonding that involves two nonmetals. It's the same side of the staircase bonding. If you think about when we talked at the beginning of the year about naming, when you have the prefixes, carbon dioxide, things like that, those are same side of the staircase compounds that actually bond by sharing electrons instead of transferring them. Because electrons are not transferred, there are no charges involved, and when you write these formulas, crisscross does not apply. So covalent bonds form between two nonmetals that are trying to get a stable octet. So they're still trying to mimic that noble gas electron configuration, but what happens with nonmetals is they're both really good at pulling on electrons, so neither one of them wants to give up electrons, and since neither one is losing electrons, since neither one's losing electrons, they're actually sharing them instead, and they're both able to claim them as part of that valence shell. So this happens because there's a small electronegativity difference between these atoms, so therefore they share electrons. Compounds with covalent bonds are often referred to as covalent compounds. However, the official term is a molecular compound. So when I tell you you have a molecular compound, it actually means you automatically have a covalent bond, not an ionic bond. And just a little terminology note, you can't actually have a molecule of salt. Just one single NaCl, for example, would actually be something called a formula unit. We don't make a huge deal about that, and we don't worry a ton about that terminology, but it is kind of important to know. When you hear molecular compound, that's actually a ding, ding, frickin' ding. You got a covalent bond, you're sharing electrons. So properties of molecular compounds, they have a low melting point. Sugar is a great example of this. You can pretty easily melt sugar, whereas salt is very difficult to melt. They do not conduct in solution. So if you put sugar into distilled water, it will not carry an electric current because there are no charges involved. And then they contain two or more nonmetals. So some of the reasons that they behave like that, or behave the way that they do. The low melting point is because there are less attractive forces. They're not necessarily as crystalline. So there are going to be fewer attractive intermolecular forces than an ionic compound, so it's easier to become a liquid. They don't conduct in solution because there are no charged particles. You need charged particles in order to have an electric current conducted. Saying they contain two nonmetals really isn't a property per se, it's just a fact about them. It helps explain why some elements are diatomic. For example, chlorine. If you have a chlorine, it's pretty highly reactive, has a pretty high electronegativity. So since chlorine is really good at pulling electrons towards itself, and it's also a fairly, not super big atom, so chlorine is going to pull on electrons really hard. Each of these guys actually have an electronegativity of 3.2. So there's a lot of attraction between the nucleus and valence electrons. So what actually happens is these guys are like, hey, we're really close to getting 8 valence electrons. If chlorine can't find anybody else to bond with, they just kind of overlap their valence shells like this. And what that actually allows them to do is they can actually both count these 2 electrons right here. So now the valence shell is 2, 4, 6, 8 for the guy on the left, and 2, 4, 6, 8 for the guy on the right. So they both feel like they have 8. We can also show this with the Lewis dot structure. 1, 2, 3, 4, 5, 6, 7 valence electrons in each of these guys. This is also often shown with a line, which is something we'll be working on. So another way of showing this is you can show 2 chlorines with a line in between them. The line represents those 2 shared electrons. And if we look at this, we can say, okay, we got 2, 4, 6, 8 electrons there, 2, 4, 6, 8 electrons there. So both of these guys feel like they have 8 valence electrons. Don't want to make those look like electrons at all. And if you do the same thing with the other diagram, that right there counts as 2 electrons. So each of those guys still feel like they have 8. Oxygen each oxygen has a very high electronegativity. Oxygen's electronegativity is 3.4, so on a scale of 4, these guys are great at pulling out electrons. They're some really small atoms. They attract those valence electrons really, really strongly. So what these guys actually do, because they have 6 each in their valence shell, when we had 7 each in our valence shell, we were able to get away with just sharing 2. These guys have less valence electrons, so they actually are going to share more electrons. So these guys are going to share 4 valence electrons and create something called a double bond. So to count these up, remember these guys in between count for both of them. 2, 4, 6, 8. 2, 4, 6, 8. So both of those guys feel like they have 8. What this actually looks like, some color to illustrate this a little bit more. 1, 2, 3, 4, 5, 6 valence electrons in this guy. 1, 2, 3, 4, 5, 6 valence electrons in that guy. So they're sharing those 4 in between them. Often, those are shown as lines. So we basically just kind of connected the dots with those. And we still have to show those other extra electrons. So if we wanted to count our electrons here, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Each of them feel like they have 8. Nitrogen has even fewer valence electrons. A nice life lesson for you is the less you have, the more you share. So since if you had 2 nitrogens show up, since each of them only have 5 valence electrons, they actually, and I know I'm sort of rule breaking by putting electrons 3 to the side, but they actually are going to share 6 total electrons. So these guys can actually bond in such a way where they have a triple bond. And now if I look at each of these guys, 2, 4, 6, 8, 2, 4, 6, 8 for each of them. So electrons can also be shared in compounds that are not diatomic. It's kind of nice sometimes to start with diatomics, but compounds bond this way very commonly. So if we started with carbon and oxygen and CO2, carbon and oxygen both have very high electronegativities. Oxygen pulls in electrons a little bit more, but there's no transfer here. They're actually going to share them. Carbon's electron configuration is 2-4, and oxygen's is 2-6. Both carbon and oxygen want to feel like they have a total of 8 valence electrons. So carbon needs to feel like it has 4 more than it does, and oxygen needs to feel like it has 2 more than it does. Looking at their electronegativity difference, or how different they are from one another, they're only different by 0.8. So that kind of tells me that these guys are likely to share electrons. And we're going to talk more about how specifically we draw these diagrams and how we know who's sharing electrons with who and all that kind of stuff. I will tell you for right now what actually happens is carbon actually has its 4 electrons like this. Each oxygen pulls up over here, and they share electrons in this configuration. So this would actually be our dot structure for CO2. Our next set of notes, we're actually going to talk about how we come up with that actual diagram. To wrap up our covalent bonding notes for today, I did a nice little, here, so you can see how these guys overlap. Those guys would overlap like that, and that would overlap like that. And now if we go ahead and count, we can see 2, 4, 6, 8. So carbon in the middle feels like he has 8. 2, 4, 6, 8. 2, 4, 6, 8. So each of those guys do feel like they have 8 in this arrangement. To wrap this up, you do need to know when we have multiple bonds, we just talked a little bit about double and triple bonds, how many electrons are being shared. So one single covalent bond is a pair of shared electrons, and it can be shown with 2 dots or 1 line. A double covalent bond, 4 shared electrons, can be shown as 4 dots or 2 lines. And a triple covalent bond, or 6 shared electrons, 3 pairs of electrons shown by 6 dots or 3 lines.